So for Chapter 5, we return to the notion that in calculus, everything is a limit. And to start off, we concern ourselves with the problem of calculating areas. So the problem is that in many cases, we need to calculate the area, or later on volume, of something with a fairly irregular shape. Now, we've taken geometry, I assume, and we were able to calculate the areas of lots of various things, like circles. That's not a circle. And, common rectangles, length times width. Common triangles, like right triangles. We had base times height, half of that. And more general more general triangles, but we needed to calculate an altitude. And then there's also trapezoids, which are essentially just triangles stacked onto rectangles. And more general geometric solids. So if I had a funky shape, for example, but it was still a polygon, then I would be able to chop it up into a bunch of triangles and calculate the area of each triangle and just add them all up, which is a lot easier if it was a regular polygon instead of this weird thing that I just drew. But we have a lot more difficulty calculating something stranger, like an ellipse. What's the area of an ellipse? Or if I chop off part of a parabola, what's the area contained in there? Or if I have a really weird shape, how do I calculate the area? Well, one way is we do what they did in the old days, is we attempt to approximate this shape using a polygon, and then calculate the area of all the triangles that make up that polygon. But this would not give us an exact answer, and depending on how we drew it, might just not give us enough. So to see how this works, we're going to start with the parabola example. So we have y equals 4 minus x squared, and I want to calculate the area of the shaded region. Now, one of the things we could have done, like in the past, is if I drew this on a really nice piece of graph paper, I could count up the squares that were inside of the shaded region, add all those up, and then I could look at all the partial squares and kind of estimate how much area those filled up. And it's not too far, actually, from what we're going to do. So I'm going to redraw it, and we're going to try to estimate it using rectangles. So I'm going to draw a bunch of rectangles in here, and I'm going to use the right-hand side of each rectangle. So I'm just going to draw some rectangles in here, and we're going to try to use them to estimate the area. So I'll draw a rectangle here. I'll draw another one here. Maybe another one here. So let's keep track of what we have. We have that rectangle, we have this rectangle. Let's maybe add another rectangle here and just use the right-hand side of that, but that's going to end up being an empty rectangle, which is probably okay because I have a little bit of overestimation on the other side. So the total area of these rectangles is I have each rectangle is of width 1, and the height of the first rectangle is actually f of negative 1. So I'll have 1 times f of 0 plus 1 times f of 1 plus 1 times f of 2. But f of 2 is just equal to 0. So what do I have here? I have 1 times f of negative 1. F of x is 4 minus x squared. So this is 4 minus negative 1 squared plus 4 minus 0 squared plus 4 minus 1 squared plus 4 minus 2 squared. But again, that's 0. So what do I have here? I have 4 minus 1, that's 3, plus 4 plus 3 again, which gives me a total area of 10. But looking at these rectangles I have in here, that doesn't seem like it's a very good estimate. So let me try to find a better balance here. What if I used rectangles which are a little bit above and a little bit below each time? So let me label this first one. And now I'll draw yet another picture. So this time I'm going to have 4 rectangles again. But this time I'm going to use the middle of each one. So I'm going to have a box. My first rectangle will be a little bit above, a little bit below, depending on which side I look. The same up here. My picture's not too great. But I'll have one box here, another box here, a third box here, and a fourth right over here. Appropriately, my picture should look symmetric, but I'm no artist. What would this look like? Each rectangle has a width 1, and the height of each one looks like it's halfway between each integer. So I'm going to have 1 times what's over here. That's minus 1 and minus 2. F of minus 3 over 2 plus 1 times f of minus 1/2 plus 1 times f of 1/2. I'll squeeze this in here, plus 1 times f of 3/2. That's what I get when I put it in halfway between each integer. And what did this evaluate to? F of minus 3/2, so that's 4 minus negative 3/2 quantity squared, plus 4 minus 1/2 squared, plus 4 minus, that's a negative 1/2, and this one's a positive 1/2, plus 4 minus 3/2 quantity squared. So these are symmetric. I end up with getting 4 minus, 9 over 4, plus 4 minus 1 over 4, plus 4 minus 1 over 4, plus 4 minus 9 over 4. So what do I end up with? I end up with 16 minus 9, 10, 11, 24ths, which is equal to 16 minus 5, which is 11. This is probably a better estimate than the 10 I got before. And I could probably get an even better estimate if I used more rectangles, because what's happening in my picture, so let's try to draw this one with 8 rectangles. I have 4 integers here, so let's try one here, one up here, one up here, and here. Oh dear. And out of each of these, I'm going to choose the midpoint again. Pictures aren't great, but you can get an idea about how if I have more and more rectangles, then these empty spaces, there might be more of them, but they're going to be a lot smaller. And if I had to estimate, I'd say that if I doubled the number of rectangles, I would at least cut the empty spaces in half. And similarly, the parts which are sticking out are going to shrink at the same rate. So if I were to have, say, infinitely many rectangles, then you could imagine that I would have 0 extra spaces and missing spaces. So doing these are what we call Riemann sums. Riemann sums are technically allowed to be arbitrary, and we'll get into that in section 5.2, but for now we have 3 major contenders for the use of Riemann sums. As we have the right-hand Riemann sum, we have the left hand, and we have the midpoint. Midpoint hand. Whatever. So the first one I did, I used the right-hand side of each rectangle to be the function value. And on the second example, I used the middle of each rectangle to be the function value. So the way this works is if we want to estimate the area under a function f of x with n rectangles, and by that I mean n is the number of rectangles I want to use, on some interval from a to b, then we divide the interval from a to b into n equal parts. And we'll do this by labeling a bunch of equally spaced extra numbers in between them. So I'll have an x sub 1, I'll have an x sub 2, dot 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 dot, up to x sub n minus 1, and I'll say b is equal to x sub n. And I'll say a is equal to x sub 0 if I need it. That way, between x sub 0 and x sub 1 is number 1. Between x sub 1 and x sub 2, that's number 2. And between x sub n minus 1 and x sub n, that's number n. So I have n equal subintervals, and I'm going to use the width of each subinterval as the width of the rectangle. So let me go back up to the picture here. I'll have an x sub I, for example, and an x sub I plus 1. And there's going to be a rectangle here going somewhere. How high does my rectangle go is the next question. So we have each width will be b minus a divided by n, because I divided b minus a into n equal parts. And we'll call this delta x, or triangle x. The next thing we need to do is we need to determine the height of each rectangle, because the area of a rectangle needs two parts, the width and the height. So the right-hand rule use the right-hand side of the subinterval. Very creative name, I know. And the left hand, you can guess, we can use the left side. And for the midpoint, we use the middle. Of each subinterval. So, if I label these, so subinterval number 1, right, left, midpoint. Subinterval number 1, this is going to be a up to x sub 1, or if I prefer, x sub 0 up to x sub 1. I'm going to use the right-hand side, that's x sub 1. If I'm doing the left, I'm going to use x sub 0, which is equal to a, and if I'm using the midpoint, I would use x sub 0 plus x sub 1 divided by 2. Subinterval number 2, that's going to be x sub 1 up to x sub 2, but that's going to be, the right-hand side of that is x sub 2, left-hand side is x sub 1, and the midpoint is x sub 1 plus x sub 2 divided by 2. And we can see a pattern emerging. So if I fill in a dot 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 right here, if I have the ith rectangle on my way to n, this interval is going to be x sub I minus 1 up to x sub I. The right-hand side is x sub I, left is x sub I minus 1, and the midpoint is the average of those two. So the area of the rectangle is I'm going to have the width, which is delta x, times the height. So if I'm using the right-hand rule, then I'm going to have b minus a over n multiplied by f of x sub I. But since these are all equally spaced, x sub I is I many subintervals away from a. So this is actually equal to b minus a over n times f of a plus I copies of the subinterval width. Similarly for the left, I'll have b minus a over n times f of x sub I minus 1. This is equal to b minus a over n times f of a plus I minus 1 copies b minus a over n. And if I want the midpoint, this looks a little bit uglier, because I'm supposed to have x sub I minus 1 minus x sub I, plus divided by 2. Oh boy. B minus a over n times, what is this going to look like in the end? A plus I times b minus a over n minus b minus a over 2n. That's what it'll end up looking like at the very bottom line. So these guys are all called Riemann sums. So the Riemann sum to estimate area is, depending on how you choose the right or the left or the middle, r sub n equal to a big sum which looks like this, b minus a over n times f of a plus b minus a, a plus I times b minus a over n. That's my width, and that's my height. L sub n equals I equals 1 up to n, b minus a over n times f of a plus I minus 1 times b minus a over n. Or using some sum properties, we'll go over those soon, I can rewrite this from 0 to n minus 1 for a simpler notation. These two sums are equal to each other. And if I want the midpoint, I'll again have b minus a over n, but I'll have f of a plus I times b minus a over n minus b minus a over 2n. So what does it look like to use these? Well, the picture is already kind of drawn into the formula here. So let's return to my parabola example. I have f of x equals, let's see, 4 minus x squared. So r sub n here, nope. If I wanted 8 rectangles, r sub 8, using the right hand rule, this would be the sum from I equals 1 up to 8. I need an interval from negative 2 to 2. That was what my picture had. X equals negative 2 to 2. So my interval here is b minus a, 2 minus negative 2, all over n. I want 8 rectangles, times f of a, that's negative 2, plus I times my b minus a over a n again. That's just plugging in my numbers. There's 1 up to 8. 2 minus negative 2, that's 4. Divided by 8 is 1/2. And sure enough, if we go back and check to the picture, if I have this interval from negative 2 to 2, and I cut it up into 8 parts, each part will have a width of 1/2 times f of negative 2 plus I times 1/2. And there's a couple of ways I could go about it from here, but since f of x is equal to 4 minus x squared, that means I would have to do, 1/2 times 4 minus negative 2 plus the first term, 1/2 squared, plus 1/2 times 4 minus the second term, this is negative 2 plus 2 times 1/2 squared, plus 1/2, 4 minus This is going to take a while to write out, so let's speed this up. Okay, so there we have a total of 8 rectangles. 1, 2, 3, 4, 5, 6, 7, 8. Perfect. So all we got to do is calculate this. No problem, right? So how good can I do this? I can factor out a 1/2. And I'd still have all of that. Let's see how far I can get without trying very hard. If I factor out a 1/2, I'll have a bunch of plus 4s all over the place. So I'll have 8 times 4 minus, but now I've got to square all of those things. That seems terrible. There's got to be a better way. Well, there is. Let's go back to how it looked before with the summation notation. If I plug this expression into the original function, to 8, I'll have 1/2 multiplied by 4 minus 2, negative 2 plus I times 1/2, quantity squared. And that's essentially what I've got listed out all over the place up there. I'll go ahead and square this out. This leaves me with, now I, if I distribute this 1/2, I minus I squared divided by 8. So I'll find out later how I can make this even shorter after this work, but now if I list out my sum, I'm going to have 1 minus 1 over 8 plus second term, 2 minus 2 squared over 8, that's 4 over 8, plus 3 minus 9 over 8, plus 4 minus 16 over 8, plus 5 minus 25 over 8, plus 6 minus 36 over 8, plus 7 minus 49 over 8, plus 8 minus 64 over 8. Wonderful. This is exactly what I would have ended up with if I had spent a whole lot of time trying to simplify the expression I had previously. What happens when I add all of this up? Well, I get 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. And that is equal to 36. Minus a whole bunch of 8s. 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64, all divided by 8. Now I just gotta plug through that. 204 divided by 8. Wonderful. Let's see if this is an integer. 204 divided by 8. I end up getting 36 minus 25 plus 1/2 after division, leaving me with 11 plus 1/2. So I got a number. And what I expect to happen is, if I take this limit to infinity, n goes to infinity of r sub n, then I should get the area. But we're going to deal with this limit next time, after covering some properties about the summation notation, so that we can have a little bit of an easier time dealing with the Riemann sum inside of a limit.